Conservation of Momentum by Taimur Aslam and Noah Solomon.
Now that we're done writing our problem, I'm going to go to read it out loud. A bullet of mass m and velocity VO is fired toward a block of mass 4m. The block is initially at rest on a frictionless horizontal surface. The bullet penetrates the block and emerges with a velocity of VO divided by 3. A. Determine the final speed of the block. B. Determine the loss in kinetic energy of the bullet. C. Determine the gain in kinetic energy of the block. Up top, you can see we have a diagram of what's going on. You have the bullet of mass m with velocity VO going into the block of mass 4m on a frictionless surface. Using this diagram, we're going to go ahead and make a before and after diagram. Okay, so now we are going to go ahead and draw the before and after diagrams for this situation. Starting with the before diagram, you have a bullet of mass m that's traveling towards a block of mass 4m with an initial velocity of VO. In the after diagram, the bullet penetrates the block of mass 4m and the block has a final velocity of VF. The bullet of mass m has a final velocity of VO divided by 3. Okay, so now that we've reviewed the before and after diagrams, we can apply these diagrams to part A, which asks for the final velocity of the block once the bullet has penetrated it. Momentum equals mass times velocity. So in the before picture, initial momentum equals mass times initial velocity. Next, we will move over to the after picture. In the after picture, initial momentum equals final momentum. And since we already have the equation for initial momentum, we need to write down the equation for final momentum. The equation for final momentum is mass VO divided by 3, which is the final velocity of the bullet, plus 4m VF, which is the final velocity of the block. We will substitute the equation of initial momentum into the equation of final momentum. And that will give us mVO equals mVO divided by 3 plus 4mVF. From this equation, since m is in all three terms of the equation, we can cancel out the mass. And that will leave us with VO equals VO divided by 3 plus 4F. From this equation, we will get 3VO divided by 3 equals VO divided by 3 plus 4VF. By subtracting the VO divided by 3, we are left with 2VO divided by 3 equals 4VF. To solve for final velocity, we will divide 2VO divided by 3 by 4. And once we do this, we will get a final velocity of VO divided by 6. Now that we've solved for the final velocity of the block, we can solve for the loss in kinetic energy of the bullet. To do so, we will simply set up the equation for change in kinetic energy. The equation for change in kinetic energy is 1/2 mass times final velocity squared minus 1/2 times mass initial velocity squared. By substituting the final velocity that we calculated in part A, we get change in kinetic energy equals 1/2 times mass times VO divided by 3 squared minus 1/2 mass times initial velocity squared. By separating terms from this equation, we get 1/2 times mass times 1/3 squared times VO squared minus 1/2 times mass times VO squared. By squaring the 1/3, we end up with 1/2 times mass times 1/9 times VO squared minus 1/2 times mass times initial velocity squared. By multiplying the 1/2 with the 1/9, you end up with change in kinetic energy equals mass times initial velocity squared divided by 18 minus mass times initial velocity squared divided by 2. By simply combining these terms, you end up with change in kinetic energy equals -8 times mass times VO squared divided by 18. And by simplifying this final equation, you end up with change in kinetic energy equals -4 mass times VO squared divided by 9.
Now that we have determined the loss in kinetic energy of the bullet in part B, we are going to go ahead and determine the gain in kinetic energy of the block in part C. Before we start this problem, just like in part B, we need to use the formula change in kinetic energy equals 1/2 times mass times final velocity squared minus 1/2 times mass times initial velocity squared. This formula is necessary because we are trying to determine the change in kinetic energy. Once we substitute the variables so that it pertains to this specific problem, we get 1/2 times 4 times mass, because the block has a mass of 4m, times initial velocity divided by 6 squared, because the final velocity of the block after the bullet has penetrated gives it a final velocity of initial velocity divided by 6, minus 0, because the block has initial velocity of 0. Therefore, we could substitute that whole part to 0. Once we simplify this, we get 2 times the mass times the initial velocity squared divided by 36. And once we simplify that into its smallest form, we get change in kinetic energy equals the mass times the initial velocity squared divided by 18 joules. Now that we have completed this problem, we're going to do a quick recap over how to find each solution. For part A, we are determining the final speed of the block. The basis of this step was to set the initial momentum equal to the final momentum, and from there substituting the variables in the equation so that you come out with the final velocity of initial velocity divided by 6 meters per second. For part B, we were determining the loss in kinetic energy of the bullet. And the basic understanding of this step was to use the equation change in kinetic energy equals 1/2 times the mass times the final velocity squared minus 1/2 mass times initial velocity squared. And once you substitute the variables in this step, you come out with the solution of -4 mass times the initial velocity squared all over 9 joules. And for part C, we were determining the gain in kinetic energy of the block. And for this step, we also used the change in kinetic formula. And once we substituted all the variables in the equation, we came out with mass times initial velocity squared divided by 18 joules. This concludes our presentation on how to solve a conservation of momentum problem.